Okay, for those of you that missed class on Tuesday, February 2nd, I recorded the class. Everybody reminded me to record it. I went and looked at it and I didn't like what I saw in the video. So I'm going to re-record this. So I apologize, I might get a little punchy, and hopefully it is not as long as what we did in class. You will need that pink sheet if you were in class. I gave this to you guys, this pink sheet. If not, it is in the Chapter 8 folder in Schoology. Okay, so you will need that chart. Our goal is to fill in that chart by the end of class today. Okay, so we started off by looking at this function, and we traced this function. And my students at first thought that this was the line y equals x, but I realized that as we're tracing that, the x values and y values are not exactly the same. Okay, so we know that it is not the function y equals x. So let's zoom out. Actually, no, I'm going to adjust the window. I'm going to make the window. I was really zoomed in on the window, so let's make the window a little bit more approachable. So I press graph. And now we realize that it wasn't y equals x. And a lot of students, everybody got that this was a sine curve. Okay? And our goal during this lesson is to represent transcendental or non-polynomial functions as polynomials. So, we did think that this function was y equals x. So let's look at that. Let's look at those two graphs graphed on the same screen. And it looks like here, for part of my screen, we're overlapping. Okay, so I'm overlapping for part of the screen, or for part of our curves. So what we want to do is let's look at the difference between those two functions. So let's go back to our y equals, and I'm going to look at the difference between the two functions. And let's just graph that. And so looking at that, I asked the students, I said, okay, what does that curve look like? And they answered exactly how I wanted them to answer. They said tangent. And I said, I agree with you. That's what I said when a previous teacher, the previous BC teacher, was teaching me this lesson. But remember what we're trying to do here. We're trying to write this as a polynomial. Okay? And then they got the idea, oh, that kind of looks like a negative x cubed. So in my y equals, I'm going to put negative x to the third. Oh no, go to. Because I did the wrong negative. And we graph those on the same screen. Okay, and it's kind of hard to see with my lighting here, but we have a purple curve and we have the black curve. We're trying to match the purple curve up with the black curve. And so we need a vertical compression. So we tried to divide by 2. And then that wasn't good enough. So we went to, then I was like, think bigger. And I think they went to 5. That's even better. And then I told them, let's try 6. I can't remember what I told them. You'd think I would remember. It was earlier this morning. And that curve matches up pretty nicely around the same x's that our sine and y equals x curve matched up. So what we have here is we have the sine of x minus x, we've said is approximately negative x to the third over 6. But remember, I'm trying to write sine of x. So I'm going to add that x over. Okay, now let's look at how sine of x and that curve compare. So sine of x and x minus x to the third divided by 6. I am going to clear that guy out. I'm going to make that guy disappear and turn that guy on. Okay, so let's now look again. And again, looks like they match up even better. So I said, okay, so let's look at the difference. So again, we looked at the difference. And by now we recognized that this looks like an x to the fifth graph, but with a pretty big vertical compression. So let's try and match that up. So x to the fifth. I think we started with like 30. I can't remember what we started with. Oh yeah, I think we did start with 30. And that wasn't good enough. So then I'm like, think bigger. So they thought bigger and we went to 60. And that matches up even better, but I know we can do better. So then one student said, well, let's try 150. And I was like, well, that's a little bit big. But I kind of gave them the answer of 120. And look at how nicely that matches up. So let's think about what we have here. We have the sine of x minus this quantity. We've said that that equals x to the fifth over 120. So again, adding that over to the other side. And then somebody recognized right away, oh, it was a great moment. I was so excited. We had the sine and they recognized that 6 is 3 factorial. 120 is 5 factorial. And that's going to mean something to us. Okay, so now I'm going to go back to here and I'm going to add in this term. I'm going to turn off this guy and we're going to clear this guy. So that was our sine curve. And now we have our polynomial approximation. And look how nicely that matches up. And something that I have in here that I actually have that's incorrect is these should be approximation signs. They're not equal signs. These are approximations. And what the class started to realize was that we had an odd power. So what we did is we kept writing a bunch of terms. And I'm going to show you plugging that in. And I know this is all very exciting. Well, I think it's exciting. I think this is actually a really cool activity. and it's kind of hard to see, but my red graph is just graphing right on top of my blue graph. Let's see, can I focus in? Can I zoom in and you guys can kind of see that? Yeah, you can kind of see that. Let's see if I can get away. See if I take away that light. That's a little bit better. It's a little bit better. My kitchen light above me is a little bright, so I was trying to make sure that. Now I'm going to zoom out. I'm going to adjust my window. I'm going to go -6 to 6. Just so that you can see how nicely, so that was my sine curve. This red curve, this curve that's now being graphed, how nicely that curve matches up with our graph. And I mean, just over here at the ends, when I get close, really close to 6, that's where it matches up, okay? So, what have we learned here? Okay, let's zoom out a little bit here. What I have learned is I now have a polynomial approximation for sine of x. So, take out that pink sheet. I have it in white just because, for a couple reasons. And write down the polynomial. So x plus minus x to the third over 3 factorial plus x to the 5th over 5 factorial minus x to the 7th over 7 factorial, and so on. So plus, and you continue the terms. Now what, and somebody in class recognized right away, well, we could write an nth term. So, first of all, I'm rotating x to the 2n plus 1. That's how I write an odd number. 2n plus 1 over 2n plus 1 factorial. Now, if I'm starting at 0, because typically we're going to be starting at 0, this becomes n. Okay? Plus dot dot dot. So again, this is a approximation. So sine is approximately this. This written as a series. You just write the nth term. And the interval of convergence, what that means is for what x values does one graph lie on top of the other one? That's for all real numbers. Okay? Now we could do the same thing with cosine. But what's the relationship between sine and cosine? Well, it's the derivative. So I can now manipulate these. I can take the derivative of each one of these terms and get my cosine function. So if I take my derivative of x is 1. For 3, I bring down the 3, reduce my exponent by 1, and reduce my fraction, because I would have a 3 on top here over a 3. Bring down the 5, reduce your exponent by 1. Hopefully you're seeing a pattern. Notice how all those exponents are negative. Oh, I was just thinking about what was on top, so it shouldn't be 2n. Plus dot dot dot. And we have our series here. So this is what it would look like as a series. And again, our interval of convergence is negative infinity to infinity. Okay? Let me just confirm that that's right. Yes. Okay. Now you're going to want to memorize these. And I told the class, okay, how do I remember these? Sine is an odd function meaning I'm symmetric. The graph is symmetric about the origin. That's why I have all odd numbers on there. Cosine, we know that that's an even graph, so that's why I have all even exponents. Okay? Okay, we're going to get to these, to the ln and the inverse tangent of x here in a minute. But I want to kind of jump around a little bit. So go to the front of the page, and let's talk about this one. So let's talk about 1 over 1 minus x. Now you may not recognize this, but this is technically the formula for sum of a geometric series. Okay, so where our first term is 1 and our ratio is x. So writing this now as a polynomial, I have my first term is 1, my ratio is x, so I just keep multiplying by x. X to the n plus dot dot dot. Few things about notation, okay, when you're writing these polynomials. You want to have this plus dot 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 plus x to the n plus dot dot dot. It's College Board's weird thing. They want you to understand that it's an approximation, a polynomial, okay? You keep adding up the terms. There's a certain amount of terms until you get to the nth term. Now writing this as a series. Okay, and I just did a quick check in my head. If I plugged in 0, I get 1. If I plug in 1, I get that term, and 2, and 3, and so on. Remember the interval of convergence for your ratio is -1 to 1. Now, I can manipulate series, okay? I can manipulate this into looking like a geometric series if I do this. Now here, our A1 is 1, our ratio is -x. Okay, so let's write our polynomial approximation. 1 multiplied by your ratio. I don't know why my brain stopped working there. Okay, so and again, your interval of convergence is the same thing. Now, understand that I have this series, and let me rewrite this over here. And again, these are approximations. Don't have an equal sign in there. I know I started the lesson off with an equal sign, and that was really bad notation on my part. Okay, so I now want to get us to inverse tangent. So knowing this, I want to get us to inverse tangent. We can manipulate these series in a lot of really, really cool ways, okay? And I think I have to give Luke credit here. It was Luke that picked out, oh, if I make this x squared. So I can substitute in an x squared. So wherever I had an x, I'm going to put in an x squared. So I put in an x squared there. X squared squared is to the 4th, to the 6th, and so on. So I still have my -1 to the n, because I keep rotating, x to the 2n. Now, what I need to get to is I need to get to inverse tangent. Plus dot dot dot, I forgot. If I integrate this with respect to x, integrate that whole thing with respect to x, hey, I'm going to get inverse tangent here. I'm trying to make it so you guys can see. Inverse tangent of x. Antiderivative of 1 is x. Antiderivative there, add 1 to your exponent, 1 over your new exponent. Add 1 to your exponent, 1 over your new exponent. Add 1 to your exponent, 1 over your new exponent. Notice how I don't have factorials here. So I have negative 1 to the n, x to the 2n plus 1, all over 2n plus 1. So again, now you want to fill this in for inverse tangent. Okay, so again, this is approximately x minus x to the third over 3 plus, ooh, this should be a 5 here. And our interval of convergence for inverse tangent is that. Okay, so now we have this. Okay, so now we're doing a good job filling in all of our values. Let's look at this ln of x1. And this is only the second year I'm using ln of x. Okay, so I need to make this ln of x1. I'm going to use... And somebody thought right away during class, if we manipulated this one and then somehow got this to be 1 over x, that's going to make our lives a lot easier. So let's look at that one, and let's hopefully, I'm kind of doing this one on the fly here, and I messed it up a little bit in class. Okay, so if I look at that, and I have to adjust that to 1 plus x minus 1. Okay, so what did I do? I substituted in an x minus 1 here. So I have a 1 minus an x minus 1 plus an x minus 1 squared minus an x minus 1 to the third plus dot 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 plus negative 1 to the n times x minus 1 to the n plus dot dot dot. So I can kind of substitute stuff in. Okay, this left side is going to simplify to 1 over x. Okay, so now we have to integrate that because we want to get to ln of x. With respect to x, remember n is just a number we're carrying along with us, so this turns into ln of x. The antiderivative of this thing is technically x minus 1. It's going to work out just better for our thing because it's the antiderivative of this thing. Okay, minus x minus 1 squared over 2 plus x minus 1 cubed over 3 minus x minus 1 to the fourth over 4. Let me make sure I'm doing that one right. I am. So plus dot 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 okay, so I now have my ln of x. 1. And I have this one on here because this is one that our book often uses. I actually have a different form of this. In our old book used ln of x plus 1. It actually works out to be a nicer formula, but I wanted to be consistent with our books. And this should be a -1 on the bottom. I don't know why it changed to plus here. It was a magic. Oh no, that should be plus. That should be plus. I apologize. And this ln of x, okay, so I had the interval of convergence basically for this thing that I translate over 1 unit to the right. So that's why my interval of convergence is that. I don't know why I started with interval notation, then I went to those. The last one we have to look at is e to the x. And I'm going to go back to what we were doing before with e to the x. Okay, so e to the x. Let's write the equation of the tangent line of e to the x at the point 0, 1. So we know y prime is e to the x. We know y prime evaluated at 0 is equal to 1. So I have y minus 1 is equal to 1 times x minus 0. So let's graph both of those. Okay. So let's graph e to the x. I don't know why I couldn't find e. And let's graph x plus 1. Okay. I'm going to look at my notes here for the good window that I need. So my window, I'm going to do -2 to 2. The rest of that stays the same. Now let's put a graph in there. So that's my e to the x. And that's our tangent line. So that's a tangent line approximation around there. Okay, so look at that. Okay, it's kind of close. Let's look at the differences like we did before. And you see, yeah, it kind of looks like a y equals x squared, but it's not symmetric. We have to manipulate that a little bit, okay? And so I told the class, I was like, hey, let's look and see. Let's go with past, what we've been doing in the past, and let's look at a 2 factorial, and let's see how well that fits. Okay, so I have e to the x minus x. We're saying that this is approximately x squared over 2 factorial. I apologize, you guys can't see that. Okay, we're saying that that's approximately. So we're saying e to the x is approximately x minus x squared plus, that. So again, let's continue with this, e to the x. Oh, I have my 1 in there. Ooh, I forgot about my 1. So let's see how well this approximates it. And that's looking pretty good. Okay, looks a little bit better, not as good over here in the negatives, but in the positives, it looks like it's pretty good. So let's now see what the difference looks like. Hey, that kind of looks like an x cubed. So let's see. Hey, what if I did x cubed over 3 factorial? Let's go here on this one, and let's add in x to the third divided by 3 factorial. And let's see how well that matches up. I'm going to adjust my window a little bit because it looked like we needed to get our y values a little bit more than what I have here. Let's do negative 3.5 to 3.5. So that's y equals e to the x. And here you see the approximation. Hey, that's looking like a pretty good approximation. So let's keep adding terms to this. You hopefully are seeing the pattern. Let's do one more. And hopefully you will see I'm going to make this, because the x's get pretty big, I'm going to make this negative 5 to 5. I didn't do this in class, so we'll see what happens here. So that's my e to the x. And it's really hard to see. Maybe I'll zoom in here. But the red graph is right on top of the blue graph. And you can always put these in your own calculator and see that one is lying right on top of each other. Okay? So it looks like our e to the x, let me zoom out. It looks like our e to the x approximation is approximately 1 plus x squared over 2 factorial plus x to the third over 3 factorial plus dot 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 plus x to the n over n factorial. And our summation is x to the n over n factorial. And our interval of convergence is negative infinity to infinity. I don't know why I wanted to write, oh, you guys can't see that. I apologize. You guys can't see that. I don't know why I wanted to write this in interval notation. I apologize. You guys couldn't see that. So now, ones you want to memorize. You want to memorize them all, okay? Geometric series, hopefully, is not too bad for you guys. This is what we call a power series. And I'll talk about what that, we're going to talk more about those. This is just the negative version of that. It rotates. For e to the x, I remember everybody in. I know it's silly. With an exclamation point for a specific reason. E to the x is everybody in. You have every single power. So you have positives and negatives. Everybody is in. Everybody's there. We're very positive about everybody being there. So all my terms are positive. I'm really excited, so I have an exclamation point about everybody being in. That's how I remember I have exclamation points at the bottom there. Okay? Okay, we're at about 35 minutes for this video. You want to make sure you know all of these power series. Okay, so you want to make sure you know all of these. The element of x one, again, I threw this one in there because our book uses it a lot in some of the videos that we're going to do. I'm not sure what shows up on the AP, I'm not going to lie to you guys, okay? But sine of x, cosine of x, inverse tangent, you want to have those memorized. along with the ones here. Okay? Okay. Thank you for watching that. I know it's long. It was like 56 minutes in class, so I took up most of the class period. So you guys get a little abbreviated. I hope that helped for those of you that missed class today.